of x is secant x, and we're supposed to find the locations of its asymptotes and its behavior near the asymptotes. So, secant x is a strange and arcane thing to say. What it means is 1 over cosine x. It's the reciprocal of the cosine function. So, if we want to know about its asymptotic behavior, we want to know where is it undefined, which means where is their division by 0, which means where does cosine x equal 0? And the answer is there's an infinite number of places where cosine equals 0, and the list starts at 90 degrees, which is pi by 2, 270 degrees, which is 3 pi by 2. What would the next one be? 450 degrees, which is 5 pi by 2, and so on. They only want the ones from 0 to 2 pi, so only these first two, pi by 2 and 3 pi by 2, interest us right now. Secant x actually has an infinite number of asymptotes, which is an idea that will give you chills, but we're just going to look at a couple of them. So let's see how this thing behaves. We'll get a number line going with pi by 2 and 3 pi by 2. There we go. All right, so the pieces of our function are 1, which is deadly boring. It's positive everywhere. I mean, that's nice, but it's not interesting. And cosine x, what does that do? If x is like 1 degree or something like that, then we're in quadrant 1 and cosine's positive. At 90 degrees, cosine hits 0. Between 90 and 270, we're in quadrant 2 or 3 and cosine's negative. At 270 degrees, cosine is 0, and if you go to 271 or any angle like that, we get positive again. And that means our function goes positive. Positive divided by 0 is undefined, negative, undefined, and positive. So, is that enough to get a sketch out of? Probably. Here's our axes. Actually, it's a waste of time having those axes on the left side because we're starting at 0, so what we really want to cover is here's 0, and then we have pi, and then we have 2 pi. That's the region we're interested in. And halfway between here we have pi by 2, and halfway between these we have 3 pi by 2. So this is 90, 180, 270, 360, if you're more comfortable thinking in degrees. I sure am. Okay, and for asymptotes, we have one at pi by 2, so here's a no-touch line. The function is scared of that. And there's another one at 3 pi by 2. And I'll just mention there's another one at 5 pi by 2. They keep on coming. And there's one back here also. There's an infinite number of vertical asymptotes for this function to dance around. And so, our function starts out positive, and it's positive up to the first asymptote. So it must have some curvature like this, where it goes up higher and higher, trying to avoid running into that asymptote. On the other side of that asymptote, the function's negative, and it stays negative all the way to the next one. So it comes up out of the negatives, then doubles back, and drops into the negatives again. It never reaches 0 because we didn't find any 0 values when we looked at this. It just stays negative. To the right of that asymptote, it's positive, so it comes down like so. And just in case you're wondering, what the shape of the secant function looks like is it keeps doubling back. It has a section that's all positive between two asymptotes, then a section that's all negative, then a section that's all positive, and it keeps alternating like that forever. That's the graph of the secant function. And if you're ever asked about the graph of the cosecant function, it's very similar, except the asymptotes are in slightly different places. But that is your shape, and you can get all that information just from paying attention to the signs and to where the asymptotes are.